Linux is a multi-user operating system, which means that multiple users can work on the same machine simultaneously or sequentially. To ensure that each user can only access what they are entitled to, and nothing more, Linux relies on a system of permissions and ownership. Understanding this system is not just a technical requirement, it is a fundamental pillar of system security, and as a future cybersecurity specialist, you will encounter it constantly, whether you are auditing a system, hardening a server, or investigating a breach. Before diving into commands and syntax, it is essential to understand the underlying model. Every file and directory in Linux belongs to a specific user and a specific group. Access to that file or directory is then controlled through three distinct sets of permissions, each applying to a different category of people. This model is called the discretionary access control model, meaning that the owner of a resource has the power to decide who can access it and in what way. The three categories of actors. Linux defines three distinct categories of actors when it comes to file access. The owner, also called the user. This is the individual user account that owns the file. By default, the user who creates a file becomes its owner. The group. Every file is associated with a group. Any user who belongs to that group will be subject to the group permissions, unless they are the owner themselves. Others, also called world. This refers to all other users on the system who are neither the owner nor a member of the associated group. These three categories are always evaluated in order. If you are the owner, only the owner permissions apply to you. If you are not the owner but belong to the group, only the group permissions apply. If you are neither, the permissions for others apply. This hierarchy is important to understand to avoid surprises. The three types of permissions. For each of these three categories, Linux defines three types of permissions. Read, represented by the letter R. For a file, this allows reading its contents. For a directory, this allows listing the contents of the directory, for example, seeing which files exist inside it. Write, represented by the letter W. For a file, this allows modifying or deleting the file's content. For a directory, this allows creating, renaming, or deleting files inside that directory. Execute, represented by the letter X. For a file, this allows running it as a program or script. For a directory, this allows entering the directory and accessing its contents. Note that having read permission on a directory without execute permission means you can see the list of files but cannot actually navigate into the directory or open any of them. It is crucial to understand that permissions on directories work differently from permissions on files. A common mistake beginners make is assuming that write permission on a file is enough to delete it. In reality, deletion is controlled by the write permission on the directory that contains the file, not on the file itself. This distinction is fundamental in security contexts. Reading permissions, the long listing format. The most common way to view permissions is to use the command lsl in a terminal. This produces a long format listing where each line represents a file or directory and begins with a 10-character string. Let us break down a concrete example. RWXRXR1 Alice Developers 4096 June 10, 10 o'clock script.sh. The first character indicates the type of item. A dash means it is a regular file. A D means it is a directory. An L means it is a symbolic link. The next 9 characters are divided into 3 groups of 3. Characters 2 to 4. RWX in our example. Permissions for the owner. Here, the owner can read, write, and execute. Characters 5 to 7. RX in our example. Permissions for the group. Here, members of the developers group can read and execute, but cannot write. Characters 8 to 10 are in our example. Permissions for others. Here, any other user can only read the file. After the permission string, we see the number of hard links, 1, then the name of the owner, Alice, then the name of the group, developers, followed by the file size, modification date, and finally the file name. Another concrete example, DRWXRX, means it is a directory. D. The owner has full permissions. RWX. The group can read and enter the directory. RX. And others have no access at all. Dash. The numeric representation of permissions. Permissions can also be expressed as numbers, which is the format used when changing permissions with commands. Each permission type is assigned a value. Read equals 4. Write equals 2. Execute equals 1. No permission equals 0. For each category, owner, group, others, you add the values of the permissions granted. For example, RWX equals 4 plus 2 plus 1 equals 7. RX equals 4 plus 0 plus 1 equals 5. R equals 4 plus 0 plus 0 equals 4. Equals 0. So the permission string RWXRXR translates to the numeric value 754. And DRWXRX translates to 750 for a directory. This notation is extremely common in system administration and security configurations, and you will need to read and write it fluently. Ownership. Who owns the file? Every file and directory in Linux has exactly one owner, a user, and one associated group. The owner is typically the user who created the file. The group is typically the primary group of that user at the time of creation, though this can be changed. Ownership matters because the owner has the unique ability to change the permissions of their own files. Only the owner or the superuser, the root account, which has unrestricted access to the entire system, can modify a file's permissions. The root user is a special account with complete control over the system. Root bypasses all permission checks. This is why it is a major security risk to run applications or processes as root unnecessarily. If that process is compromised, the attacker gains full control over the system. This concept is known as the principle of least privilege. Every user and process should operate with the minimum permissions necessary to perform its function. Why this matters in cybersecurity? A misconfigured permission is one of the most common sources of security vulnerabilities in Linux systems. Consider the following real-world scenarios. A web server configuration file containing database passwords is readable by all users on the system. Permissions set to 644 or even 777. Any user who can log in can read the credentials and compromise the database. A script that is executable by all users but writable by all users as well, permissions set to 777, can be modified by a low-privilege attacker to include malicious code that will later be executed by a more privileged user or automated process. A directory that is writable by everyone allows any user to delete or replace files inside it, even if those files are owned by someone else, because deletion rights come from the directory's write permission. A binary file owned by root with a special set UID bit, a more advanced concept you will study later, can allow a regular user to execute that program with root's privileges, which, if the program is vulnerable, becomes a direct path to privilege escalation. During a penetration test, one of the first things an auditor does after gaining access to a system is look for files and directories with overly permissive settings. Tools and manual commands help identify world-writable directories, files owned by root with dangerous permission combinations, and sensitive files readable by unauthorized users. The default permission mask. When a new file is created, it does not receive arbitrary permissions. Linux applies a default creation mask called the umask. The umask defines which permissions are removed from the default. By default, files are created with a base of 666, read and write for all, and directories with a base of 777. The umask value is subtracted from these defaults. A common umask value is 022, which results in files being created with permissions 644, owner reads and writes, group and others read only, and directories with 755, owner has full access, group and others can read and execute. Understanding the umask is important in security hardening. A poorly configured umask can result in sensitive files being created with excessive permissions. Summary of key points to retain. Linux permissions control access for three categories: owner, group, and others. There are three permission types: read, R, 4, write, W, 2, and execute, X, 1. Permissions on directories have specific meanings that differ from file permissions. Permissions can be expressed symbolically, RWXR, or numerically, 754. Every file has one owner and one associated group. Only the owner or root can change a file's permissions. The root account bypasses all permission checks and must be used with caution. Misconfigured permissions are a major source of vulnerabilities in Linux environments. The umask controls the default permissions applied to newly created files and directories. With this foundation, you are ready to learn how to actively change permissions and ownership using the appropriate Linux commands, and to understand how these concepts apply directly to security auditing and system hardening tasks.